Here I have a picture of some balloons. These balloons are each tied to a string, and then that string is tied up to a paper clip overhead. Here's an experiment that you can try at home. Grab two balloons, rub them both on your head like this, get them nice and staticky, tie them to a string, and you'll see that they hang like this with some space in between them. If we wanted to draw a free body diagram of these balloons, then we totally could. Wait, let me move this. If we wanted to draw a free body diagram of these balloons, we totally could. Here's what we would do. Pen. Let's use green. We'd say that there is most definitely a force pulling each of these balloons down. And the force pulling down on each of these balloons would, of course, be gravity. So we say this is F, G, and this one is also F, G. The string is also pulling up on this balloon like this. So we'd say that there's another force on this balloon, and that other force is the force from the string. I'm going to call it Ft for the force of tension, or you could also call it F string would be fine. But then there's another reason why, there's another force acting on these balloons. There's a reason why these two balloons aren't just squishing together. And it's because there is a force of repulsion between them. A force that pushes this one, whoa, oh my, that was a lot. Nope, okay, well, I guess it's just going to be crooked. A force that pushes this one this way, and a force that pushes this one this way. That force is what we call the electrostatic force. And we represent it with the letter F, E. F, little e. And, whoa. And that is our topic of the day. Today, clear? Okay, cool. Today, we are going to be talking about the electrostatic force and Coulomb's law. Now, when it comes to the electrostatic force, we actually know that in reality there are four fundamental forces. Here are the four fundamental forces. The first, I'm going to change my color here to keep it nice and interesting. Let's go blue. The first of the four fundamental forces is, got it? Nope, don't got it. Try again. Okay. First of the four fundamental forces is gravity. Gravity is the first of the four fundamental forces. Gravity, we have already talked about pretty extensively. You know that there are two formulas for gravity. One formula for gravity is Fg is equal to mg. And the other formula for gravity is wait, you could do it, G is equal to capital G times m1 times m2 all over r squared. We use these different equations in different circumstances. We know that gravity is the force of attraction between any two objects with mass. We know that mass creates this force of attraction between other objects with mass, that all mass pulls together. This first equation, you know, we use when we have a situation of an object that has a mass m and it's sitting on the surface of the Earth or on the surface of some planet where the acceleration due to gravity on that particular planet is g. This is the equation for finding the force of gravity on a specific object because of a specific planet that has a specific acceleration due to gravity g. This second equation we can use for any two objects with mass. So this capital G, you'll remember, capital G is our universal constant of gravitation. It's equal to 6.673 question mark times 10 to the negative 11th newtons meters squared per kilogram squared. Nice little concept there. That's times 10 to the negative 11th here, not times 10 to the negative, or not times 10 to the 71st. Oh, wait, I need an eraser. not you. An eraser. Yes. Okay, try again. Yay. Okay, we'll fix that up. You know that the second equation can be used between any two objects with mass, where G is this constant, M is the mass of the first object, M2 is the mass of the second object, and R is the distance between them. I could use this equation to find the gravitational force between a mango and a pineapple, which there is a gravitational force between a mango and a pineapple. This one only works for objects on the Earth or objects on a planet. This could be for the Earth and the sun. This could be for the Earth and the moon. This could be for a mango and a pineapple. It could be for any two objects with mass. That's the first of the 4 fundamental forces. As you know, there are 3 more. The second one that I want to talk about today is not actually the second one on the list. The second one that I want to talk about today is the electroweak force and the electrostrong force, or what we call the nuclear weak force and the nuclear, we are so laggy today, wow. The nuclear strong force. This is like when you watch it at like 5 times speed, as you just wait for the lag to catch up with me. Okay. The nuclear weak force, you really do not have to know much about that for today. All that you really have to know is that it exists. What it really is it's the force that controls what quark a quark is, and it determines whether or not a quark turns into another type of quark. And if you're saying, Miss Wilson, what even is a quark? Well, a quark is a part of a proton. Like, a proton is not all that there is. If you break down a proton into its parts, we see that protons are made up of quarks. If you break down a neutron into its parts, we see that neutrons are made of quarks. The nuclear weak force determines what kind of quark something is, and it's responsible for turning one type of quark into another type of quark. But you really don't need to know about that. What you need to know about the nuclear strong force is that the nuclear strong force is responsible for holding protons and neutrons together in the nucleus of an atom. It kind of acts like a glue that keeps those protons and those neutrons stuck together so that the nucleus of the atom doesn't go flying apart. And finally, the last fundamental force, the last of the 4, is the one we're talking about today. It's the topic of the day. It's the electromagnetic, I feel like the sloths in Zootopia. The electromagnetic force. The electromagnetic force. Now, just like gravity has a formula that we can use to find it, that we can use to find the force due to gravity, the electromagnetic force also has an equation that we can use. And that equation looks something like this. We say that the strength of the electromagnetic force is equal to K Q1 Q2 over R squared. Where here, K is a constant. This constant, I shall write over here. I'll just write it. My space. Okay, I'm just gonna write it over here. Oh gosh, nope, I'm erasing. I'm so sorry. Oh, wow, this is just embarrassing. Okay, sorry to take so much of your precious time. But you will actually need that number later, so I hope you wrote it down. Bye. Okay, we're almost there. Almost good. Almost good. Almost cleared out. Thank you for your patience. I hope you've sung a song by now or something to keep yourself entertained. Okay. Here's what you need to know about these constants. You got K. K is known as Coulomb's constant. Coulomb's constant. And K is equal to 8.99 times 10 to the 9th newtons meters squared per kilogram squared. 8.99 times 10 to the 9th newton meters squared per kilogram squared. Q1 is the charge on the first object. Q2 is the charge on the second object. And r is the distance between the objects. Okay. This equation is so significant that it actually gets its very own special name. We call this equation, if I can box it perfectly, close to perfectly, we call this equation Coulomb's law. Coulomb's law. And Coulomb's law shows the strength of the electromagnetic force, or sometimes called the electrostatic force, between two charged objects. The electrostatic force is the force that's responsible for either pulling two unlike charges towards each other or pushing two like charges away from each other. If I put a positively charged balloon next to a positively charged balloon, it's the electrostatic force that's going to cause them to repel. If I put a positively charged proton next to a negatively charged electron, it's the electrostatic force that's going to bring them together. We see that the electrostatic force, or the electromagnetic force, is very, very similar in its equation format to the gravitational formula. The gravitational formula gives you G m1 m2 over r squared. The electrostatic force gives you K, a constant, times Q1, Q2, the two charges, divided by r squared, the distance between them. Both gravity and the electrostatic force act very, very, very crazy similarly. And that should just strike you in some way. That should hit you as very interesting and also very simple. Like, isn't it very simple to say that the force between two balloons that would push two balloons together because of static electricity has a very, very similar format to the force that would hold together the Earth going around the sun in our solar system? Those two forces are crazy, crazy similar. And it turns out that the universe is sometimes a pretty simple place where things are actually more similar than you might think. Even though they're totally different topics and you have totally different things at play, like charges versus mass, really, at the end of the day, they operate according to the same principles and rules. There is a whole philosophy of science dedicated to this that likes to think about science in terms of beauty and simplicity. That the true answer should be something that is nice and simple. And we most certainly see that reflected here, where the equation for the electrostatic force is so crazy similar to the equation for the gravitational force. Now, a few other things here. Let's talk about sign conventions. It turns out that any force has direction, and the electrostatic force is no exception. It should have a vector hat over the top. Now, here's what I want you to notice. If Q1 is positive and Q2 is positive, if you have two positive charges sitting next to each other, those two positive charges will push away from each other. And the net force will be, or the force between them will be positive, because you've got a positive times a positive. If you had two charges that were negative, you have a negative Q here and a negative Q here, then the force will be positive, because a negative times a negative equals a positive, and they will push away from each other. But if you have two unlike charges, if you have a positive here and a negative here, the positive and the negative will create a force that is negative, and those two things will push towards each other. They'll be pulled inwards. This gives us a sign convention that I'll write here in purple. That is true for the electrostatic force. Here's what we say. We say that a force is positive if it is a repulsive force. A positive electrostatic force means those two objects are pushing away from each other. Those two objects don't like each other. A negative electrostatic force is an attractive force. It means those two charges are moving towards each other. They're being pulled towards each other. This is true not just for the electromagnetic force, but also for gravity. If you look at the AP equation sheet for physics does not have, oh gosh, come on, we can do this. Okay, sorry team. The AP equation sheet for physics does not have the equation that you just saw for gravity. It does not say that the acceleration, or that the strength of the force of the gravitational force is equal to Gm1 m2 over r squared. That's not what it says. What the AP equation sheet says is it says that this is true. Fg equals negative Gm1 m2 over r squared. The reason why this negative is here is because gravity is always an attractive force. Mass is always going to pull on other mass. And so our equation for gravity accounts for this by throwing a little negative sign in the front. So in our electrostatic force, the sign comes out as either positive or negative. Positive meaning those two objects are pushing each other apart. Negative meaning those two objects are pulling each other together. For gravity, it always comes out to be positive here. Or it always comes out to be negative here, showing that it's always an attractive force. Now, please go ahead and draw in your notes a little helium atom. And I will do the same. You're probably already done by now. You're like, I've drawn like a gazillion helium atoms at this point, Miss Wilson. Okay, let's draw a little helium atom. I'm going to draw it over here. This little helium atom is going to have a proton. It's going to have another little proton. It's going to have a neutron. It's going to have another neutron. And then it's going to have, orbiting around the outside, okay, that wasn't terrible, 2 little electrons hanging out. Can you please check your notes and see what of the 4 fundamental forces are at play here? First, you should say, well, the nuclear weak force is likely somewhat at work. That one we really haven't talked much about, but it's like doing stuff with all the quarks, and you could say, okay, so maybe that's happening, maybe it's not. But you should say the nuclear strong force is definitely acting here. The nuclear strong force is holding these protons together, and it's holding these neutrons together. You should also say, it looks like the electromagnetic force is also at work here. Isn't the electromagnetic force pushing these 2 protons away from each other? They stay together in the nucleus because the nuclear strong force wins, so they stay together. But the force of the electromagnetic force is actually pushing them apart. Likewise, you should say, well, the electromagnetic force is also pulling this negative charge towards this positive charge, and pulling this negative charge towards this positive charge, and this positive charge towards this negative charge. So you have the electromagnetic force that's acting. Lastly, you also have gravity acting because you have this neutron has mass, this proton has mass, this electron has mass, and anything that has mass is pulling towards anything else that has mass. So these protons are pulling each other by gravity, this proton's pulling on this neutron by gravity, this electron's pulling on this neutron by gravity, and you get the gist. Everybody's pulling on each other by gravity. So you can see that lots of our forces here are at play. Here's the question. This proton is pulling on this electron by gravity. This proton is also pulling on this electron by the electric force. Which one is stronger? Shall we find out? Let's take a look at, instead of a helium atom, which is slightly more complex, let's take a look at a very, very simple atom, a hydrogen atom. Because a hydrogen atom is so very simple. It's just 1 proton surrounded by 1 electron here. Now here are a few things you would need to know. If you wanted to know which one's stronger, the gravitational force or the electric force, you would need to know a few things. First, you would need to know the mass of a proton is equal to, I do believe, and this is off the top of my head, so is it right? I'm not really sure, but I think it's 1.67 times 10 to the negative 27th kilograms. You would also need to know the mass of an electron. The mass of an electron is equal to 9.11 times 10 to the negative 31st kilograms. That's a negative 31 there. 9.11 times 10 to the negative 31st kilograms. You would also need to know that the radius of a hydrogen atom varies, but the radius of a hydrogen atom is on average about 5.22 times 10 to the negative 11th meters. You would also probably want to know a few other things. You'd want to know the charge on the proton and the charge on an electron. Well, the charge on a proton, QP, is equal to positive E, which is equal to 1.602 times 10 to the negative 19th. Coulombs. You would want to know the charge on an electron. Well, the charge on an electron is just equal to negative E, which is equal to a negative 1.602 times 10 to the negative 19th coulombs. And I do believe that's all that you would need to know. Let's go ahead and try it. We'll start by finding the force due to gravity that pulls this little electron and this little proton towards each other. Here's where we would start. We would start by saying that the force due to gravity acting between them is equal to negative gm1 m2 over r squared, like this. Then we'll plug in numbers here. When you plug in numbers, you have to remember what g is. G is 6.673, I believe, times 10 to the negative 11th. Newtons meter squared per kilogram squared. Then you would plug in the mass of the proton, which is 1.67 times 10 to the negative 27th kilograms. Ooh, we're tight on space here. Then you would plug in the mass of an electron, which is 9.11 times 10 to the negative 31st kilograms. Sorry again about my lag. My lag today is terrible. Divided by r squared. Our r here is 5.22 times 10 to the negative 11th meters. Do not forget to square this here, especially when you type it into your calculator. Oh my. We are just going crazy. Okay, let's all relax. Everybody relax. Okay, meters squared. When you plug it into your calculator, don't forget the squared there. Plug it in and see what you get. And I actually forgot my calculator, so I gotta run and grab it real quick. I'll be right back. Okay, got my calculator. When I type this into my calculator, do not forget the negative sign here. I get negative 3.73 times 10 to the negative 47th. Oh my. 10 to the negative 47th newtons. Check it out. I like that there's a negative sign in the front because that means it's an attractive force, which is true. I also like that I landed with newtons. Check it out. This force here is really, really, really crazy small. 10 to the negative 47th, that is like a teeny tiny force. Let's go ahead and calculate what we get when we try the electric force. The electric force is equal to K Q1 Q2 over R squared. No need to put a negative sign in front this time because the signs of our charges will take care of it for us. When we plug in numbers here, our K is equal to 8.99 times 10 to the 9th newtons meters squared per coulomb squared. Q1, sorry again, my handwriting's a little messy because I'm writing before the lag loads, so I'm writing before I can see what I'm writing. It's kind of crazy over here. Q1 is going to be equal to positive 1.602 times 10 to the negative 19th coulombs because it's the charge on a proton. So I'm going to write positive 1.602 times 10 to the negative 19th coulombs times, now the charge on my second object this time is an electron. It's going to be negative 1.602 times 10 to the negative 19th coulombs. Divide that all by my radius squared. My radius is equal to Oh, wait. I need to move this little thing out of the way. So sorry. Doop-a-doop-a-doop. Slide up here, please. Thank you. My radius is equal to 5.22 times 10 to the negative 11th meters squared. So I plug in 5.22 times 10 to the negative 11th meters. All of that is going to be squared. Plug that into your calculator. This is the time where you take out your calculator and you plug it in. And you should get something like negative, I believe, 8.47 times 10 to the negative 8th newtons. Once again, notice the negative sign is good here because it's showing that there is an attractive force between this electron and this proton here. Also, it's to the negative 8th, which means it's very, very small. The final units are in newtons, which feels nice to me because every unit of force ever should be in newtons. Now, here I have a small number, and here I also have a small number, but which one's smaller? Gravity, by a long shot. It's times 10 to the negative 47th. This one's times 10 to the negative 8th. Here's something I want you to do. I want you to take, let's change up our color just slightly here. I'm going to make it, wait for it, a lighter red. Try this. Can you do the electric force between the proton and the electron divided by the gravitational force between the proton and the electron and find out what you get? Go ahead and type that into your calculator. When you do, you should get, I believe, 2.27 times 10 to the 39th. Ooh, my 39 is bad there. Oh gosh, I turned off my webcam. Come back, me. Oh, there I am. Haha. It's going to be 2.27 times 10 to the 39th. Here's what that means. That means the electric force between this electron and this proton is 2.27 times 10 to the 39th times greater than the gravitational force between them. That's insane. The electric force is way, way stronger than the gravitational force. If you were to ask the question, what holds the proton and the electron together in the atom? Why doesn't the electron go flying off into space? The answer is really not gravity. Gravity plays very, very little role. The answer is almost entirely the electrostatic force. The electrostatic force does the brunt of the work of holding together that little positive charge and that little negative charge. And yet, as weak as it is, gravity holds our whole solar system together. Isn't that nice? And that is all for today, ladies and gentlemen. Whoa, right at the bell! That is pretty awesome. A quick recap for you. We started by talking about the 4 fundamental forces. We talked about what each one does. We talked about the formula for the electric force, which is Coulomb's law. Then we compared the gravitational force and the electric force inside of a little hydrogen atom. And that was the gist. So there you go, ladies and gents. Hope you have a wonderful, wonderful rest of your day. Bye, good people.